Hello. In this lecture, we're going to um, consider shafts that are subjected to both twisting moment and bending moment. And when the shaft is subjected to both twisting and bending moment, the shaft must be designed on the basis of the two moments simultaneously. Alright, and there are two approaches to that. And the first one we look at is the maximum shear stress theory, or the Guest theory, and that is used for ductile material such as mild steel. There's another one called the maximum normal stress theory, or the Rankine theory. The Rankine theory is used for brittle materials like cast iron. Alright, so let's look at the maximum shear stress theory, which is the Guest theory. And it states that the maximum shear stress in the material or in the shaft is equal to 1 on 2 times the square root of the bending um, moment in the material square plus 4 times the shear stress in the material square. Alright, so here you will see the presence of bending moment, and you see the presence of the shear stress or bending stress and the shear stress. So we have the maximum shear stress theory is equal to, or the maximum shear stress theory states that the maximum shear stress in the material or in the shaft is equal to 1 over 2 times the square root of the bending stress in the material square plus 4 times the shear stress in the material square, 4 times the square of the shear stress in the material. Alright, then if we substitute this value here, we know this value, shear, we know this equation here, that the torque is equal to pi on 16 times the shear stress times the diameter of the shaft cube. Now we also know this bending moment formula. The bending moment is equal to pi on 32 times the bending stress times the d exponent 3. Alright, so in this, if we make the shear stress here the subject, and then here we make the bending stress the subject and substitute them into this equation, we are going to have this equation here. If we simplify, we'll obtain this equation. So in this case, we have the maximum shear stress in the material to be equal to 16 on pi d cube times the square root of the bending moment in the material square plus the torque square. Alright, then if we limit the maximum shear stress to be equal to the allowable shear stress for the material, then we are going to have this. And bear in mind that this expression here, the square root of the uh, the bending moment square plus the torque square, this expression is known as the equivalent uh, twisting moment, the equivalent twisting moment. All right, so the equivalent twisting moment TE is equal to the square root of m square plus t square. All right, and that should be equal to this expression here. So what we've mainly done here is to limit the maximum shear stress to be equal to the allowable shear stress in the material. So we say that this now become the tau, which is the allowable shear stress. So if we make this expression the subject, or the equivalent twisting moment the subject of this equation, then we are going to have the equivalent twisting moment to be equal to 16 times pi d cube times that, and then divided by 16, as we have over here. All right. Then uh, according to the maximum normal stress theory, the maximum normal stress in the shaft or in the material um, is equal to this equation. So here we have maximum normal stress or maximum bending stress in the material. You know that the bending stress is a normal stress, all right, in the material is equal to half times the bending stress, that is the allowable bending stress, plus 1 on 2 square root of the allowable bending stress square plus 4 times the square of the allowable shear stress in the material. Right. Then again, if we substitute these values here, making the tau the allowable shear stress here the subject of this, and then make the allowable bending stress here the subject for this. If we substitute that into this equation here and we simplify, we are going to obtain something like this. So here, make this the subject, that the subject, and substitute into it and simplify. We'll get something like this. Again, this one here is what we call the equivalent bending uh, stress or moment. All right, so equivalent bending moment. So this equivalent bending moment here is equal to the um, the expression that we have here, pi on 32 times the bending stress times d cube, and that is obtained by limiting the uh, bending moment, the maximum bending moment, to the allowable bending moment. All right, so if we say that we limit this maximum bending moment to the allowable bending moment in the material, then it means that we are going to have the equivalent bending moment in the material to be equal to this expression, where this one becomes the allowable bending moment in the material. All right, so let's look at this equation here. It says that a shaft supported at the end in ball bearings carries a straight tooth spur gear at its midspan and is to transmit 7.5 kilowatts at 300 rpm. The pitch circle diameter of the gear is 150 millimeters. The distances between the center line of the bearings and the gear are 100 millimeter each. If the shaft is made of steel and the allowable shear stress is 45 megapascals, determine the diameter of the shaft. Show in the sketch how the gear will be mounted on the shaft. Also indicate the ends where the bearings will be mounted. The pressure angle of the gear may be taken as 20. So here is 20 degrees. So the pressure angle may be taken as 20 degrees. So this one should be 20 degrees. All right. Okay, so in a situation like this, we first need to obtain the layout of the shaft and then see how the loading is. Then we can start with the calculations. Okay, so let's look at um, 8. So we have, first of all, we have been given the power to be transmitted. So we have the power to be transmitted, P, to be equal to 7.5 kilowatt. Then we have the speed to be equal to 300 rpm. Then the race diameter, the diameter for the pitch circle diameter for the gear is giving us 150 millimeters. So let's use D for that. So D is equal to 150. Then we have the distance, all right? The distance from the center of the gear to the bearing from each side is 100 millimeters. So the total span of the shaft is going to be 200. So let's use L to represent that. So say L, which is the length of the shaft, is equal to um, 200 millimeters. Then the allowable shear stress in the material has been given as 45 megapascals. Then we also have the pressure angle. We're given the pressure angle. Let's use the pressure angle for the gear is 20 degrees. So let's use alpha to represent the pressure angle. So we have 20 degrees. That's 20 degrees. Okay. So with this information, first we need to get the general layout of the shaft. So the layout of the shaft, um, we have in the question it has been stated that the pitch circle diameter of the gear is 150 millimeters, and the distance between the center line of the bearing and the gear are 100 millimeters each. So first, let's indicate. So we have known that 100 millimeters from the center of the gear to both sides, and then this shaft is supported by bearings at the end. It carries a straight tooth spur gear and it mid-span. So the spur gear now is mounted at the middle of the shaft. So let's say that we have Right, so let's take this diagram as the layout of the shaft. And from the equation, the distance from the center of the gear to the center of the bearing, to the left side is 100 millimeters and to the right side is 100 millimeters. Then this gear is having a pitch circle diameter of 150 millimeters. So the pitch circle of the gear is that circle in the middle of the gear where the power is usually transmitted during the operation of the gear. All right, so that is the diameter which has been given to us. And the pressure angle has been given to us as 20 degrees. So what we have to do first of all is to determine the torque on the shaft. And we know that the torque on the shaft T is equal to torque on the shaft T is equal to 60 times the power P divided by 2 pi n. All right, so if you put the values that has been given to us, 60 times the power is 7.5 kilowatt divided by 2 pi n, where n is 300 rpm. If we compute that, we are going to get the torque on the shaft to be equal to 238.732 Newton meters. All right. Now, having obtained this, we need to determine the loads or the forces on the shaft. Because we have a gear on the shaft, these gears will exert some forces on the shaft, and to be able to determine those forces, let's try to sketch the layout of the shaft of the gear and I try to determine how the forces will be acting on it. So let's say that we have this circle here which forms the form of the gear. So we have a gear teeth on it. All right, so let's the gear teeth on it is like that. Now this gear that we have here to transmit the load from or to transmit the power from the source where it's coming from through the gear to the shaft, it acts along what we call the pitch circle. A pitch circle is usually at the center of the gear teeth. So somewhere the pitch circle lie around this area here, which has been given to us. All right, and the actual load on the teeth is usually normal to the surface of the gear tip. So like this one, you can have the load that will be acting on this gear to be at an angle of 90 degrees to the face of the gear. All right, that is the normal load on the surface. So we can say that the normal load will be acting in this direction. All right, it's acting in this direction. It's acting in that direction. Then there will be another load. All right, this load has to be resolved into two. The load that transmit the power or that provide torque to the gear, which is transmitted through the shaft, is tangential to the gear. All right, so that load is tangential to the gear or tangential to the pitch circle of the gear, and we can represent that from here. So you can say that that load is being transmitted in this direction. All right, and then there will be another load which will be what we call the radial load, and this radial load is transmitted um, in a vertical direction. It goes like that. So the radial load goes in that direction. So here, this one, let's call it the WN, the WN. That is a normal load on the face of the gear. Then this one here, let's call it um, FT. So let's say here is FT. Sorry, FR. Let's call it FR. Then there will be another load also will act in this direction. There will be another load which is acting in a tangential direction. Let's call that FT. So this FT here is a tangential load which will bring the torque to the system. All right, because we know that the torque is equal to the uh, force, which is the tangential force times the radius. All right, so this Ft is what will bring the torque, and this Ft is tangential to the pitch circle. All right, now the angle between the Fn, the Wn, which is the normal load, and then the tangential is what we call the pressure angle, and that is this angle here. So this angle is a pressure angle, which we call the pressure angle, and that is the alpha. All right, and in our case the alpha was given to us to be 20 degrees. So what we have to determine now is the Wn, because the Wn will be the bending load on the shaft. That is the load that will bring bending to the shaft. So if we take the center of the gear to be this point, this load here is what to be the resultant of the radial load and then the tangential load, and that will be what will bring the actual bending. Actually, we'll have bending from effect from the radial load Fr, and we also have bending effect from the Ft, which is the tangential load. But we could determine this one and have the bending moment for it, and this one and having the bending moment, and finally we superimpose the two. Or we could just determine the resultant Wn, that will find the bending moment with respect to the Wn. So what we are going to do now is to determine the Wn. When we can only do that if we're able to obtain the Ft, which is the tangential load in the system. All right. So first of all, we know that is this tangential load which produced the torque. Is the tangential load that produced the torque in the system. So if the tangential load produced the torque in the system, we already have our torque here. All right. So if we have the torque, then we can determine the Ft using the formula. We know that the torque T is equal to we have the force Ft, all right, Ft um, divided by, sorry, it's going to be Ft times r, the radius, all right, the radial distance, which is d on 2. Which is d on 2. All right. So in this case, we are going to have Ft to be equal to 2 times the torque divided by d, and that should give us, we know the pitch circle diameter d to be 150 millimeters, so we have to change it to meters. So we have 2 times 238.732 divided by the d, 0.15, and if we compute that, we'll get Ft to be equal to 3,183.093 in newtons. Now, having obtained that, we can now determine the normal load on the face of the gear. All right. So the normal load on the face of the gear, we can determine that by simply using trigonometry. So in this case, we can say that the normal load, because here we have the Ft, which is the adjacent, and this is the hypotenuse, the normal load. All right, so we can say that Ft is equal to Wn cos alpha. All right, so here Wn is equal to Ft divided by cos alpha, and that will give us 3,183.093 divided by cos 20, and when we compute that, we're going to obtain the Wn to be equal to 3,355.451 newtons. All right, So that gives us the value for Wn. Now, having obtained this value, we can go ahead to determine the bending moment on the shaft. And when we look at the outline of this of the loading on the shaft, we can say that this shaft, the maximum bending moment will occur at the center of this shaft. All right, the maximum bending moment will occur at the center of the shaft. We will have reaction forces at this point, and then at that point, and then Wn, our Wn is acting in the middle. So we have reaction force here, and then another one here, and then we have our Wn, which is the load, the normal load. It will be acting in the middle. If you are looking at the gear from this direction, you will have it acting in the middle, this direction. So that is the Wn. So this Wn, it will subject the shaft to bending, and the maximum bending moment for this particular loading, because the load is point load acting in the middle of it, the maximum bending moment will occur in the middle of the shaft. So by inspection, we can say that that will be the case. So let's say that we have this reaction here. If this is Fwn, then the reaction at this end here will be equal to the reaction here will be equal to Wn on 2, and the reaction here will also be Wn on 2. All right, that will be the reaction at both ends. Just divide this to share. All right, so we divide the Wn into 2, and that will be, divide that into 2, that will be the reaction at both ends. And if that is the case, then we can determine the bending moment, the maximum bending moment. And you should note that the maximum bending moment is what we use in determining the size of the shaft. All right, so from that, we can say that the bending moment M, the bending moment M is equal to Wn times the length. All right, so we are picking one distance, we are picking one reaction, so we could determine the bending moment from the left or from the right. So we have this force here, this force times the distance from here to the middle. So if you call this one here to be L, which is equal to 200, the total length of the shaft 200 to be L, then half of that L, right, L on 2 times the reaction Wn on 2. So you will have it to be equal to Wn times L divided by 4, all right, which is simply Wn on 2, which is Wn on 2, Wn on 2 times L on 2. and that is mainly W and L on 4. And this L here should be in meters. So Wn, we have the value 3355.451 times 0.2, which is the length of the shaft, divided by 4. And after computing that, we are going to have the bending moment to be equal to 167.773 Newton meters. I always make sure that I use the right unit. Now from here we can calculate the equivalent bending moment, or the equivalent twisting moment, sorry. So equivalent twisting moment, when we are using the maximum shear stress theory, we need to determine the equivalent twisting moment. So TE, you know that TE, equivalent twisting moment, TE is equal to the square root of m square plus t square plus t square. Alright, the bending moment square plus the torque square. And that should give us the square root of the bending moment 167.773 square plus the torque, and the torque we have calculated it earlier to be equal to 238.732, also square. Then when you simplify that, you get the torque, the twisting moment, the equivalent twisting moment to be equal to 291.789 Newton meters. Then we know that the equivalent twisting moment TE is equal to pi on 16 times tau, which is the shear stress, the allowable shear stress in the material, times the cube of the diameter. So what you're interested in this case is the diameter here. We already know the TE, the allowable shear stress was given. So we can now calculate for the diameter. So diameter will be equal to the cubic root of 16 TE divided by pi times tau, and that should be the cubic root of 16 times 291.789 divided by the allowable shear stress, which is, we have allowable shear stress, which is 45 times 10 exponent 6 times pi. And when you simplify that, we'll get the diameter D to be equal to 0.03208. which is simply, this is in meters, which is simply 32.08 meters, 32.08 millimeters. All right, so this one, again, and go to the standard table, we'll see that the value we can get is 35. That's the standard value. To always make sure that the standard diameter you select is not less than the value that you've calculated for. So it should be the next one, the next largest number from what we have calculated. So we can say that the D um, is equal to, or approximately, is 35 millimeters. Right, so that gives us the final answer. And of course, this we use the maximum shear stress approach to obtain this. And if you use the maximum uh, normal stress or the maximum bending stress approach, you are going to have a value that will be a little bit different from what we have obtained. So what you can do is to uh, go through the processes again, but this time using the maximum normal stress formula, and see what you will get. Thank you very much. See you later.